today I will connect the two, the hill slope and the fluvial processes, but with more emphasis on the fluvial processes, but just focusing on what's going on the coarse sediment load, how it is transformed, how it evolves from the upper part of the drainage system down to the foreland basin. So, why it is interesting to, or even important to look at grain size? Because you could say, okay, it's just sediment, so we don't care it's small or large. We just look at flux. It's what we have done so far. We have just been looking at erosion rate, sediment flux, whatever it was in small or large size. But we saw, for example, that for fluvial transport, we got a sediment flux function or transport capacity, which is depending on a critical shear stress. And this critical shear stress will depend, the shear stress is depending on the diameter size or the diameter of the grain or the particle you are transporting. It means if you are, for example, in transport limited or even in hybrid river, if you have to transport fine grain size, so you can do, or the river can do it by, or achieve it by having a weak or low gradient. If it's coarse grain size that the river has to transport, then the river gradient will be will have to be steeper or larger. So we saw that for the fluvial transport, pebble size or particle size is a big deal. Then we will see that when we try to interpret sediment archives, well, in all kind of sediment studies, in whatever it is in tectonic or in looking at climatic evolution, it is fundamental to understand what is the transformation of the sediment between the source and the sink. So we saw yesterday, for example, that during the transport in the foreland basin, the sediment, the fine sediment, are transformed by weathering, losing mobile elements like sodium or potassium. So when you go and you look at some sedimentary archive, the sediments you are looking, it's not a direct translation on what's going on the hill slope, but maybe this sediment has been affected by some transformation. What is it? A chemical transformation or a physical transformation? And this transformation can have introduced some bias, some difference between the initial product and the one you are looking in your sedimentary archive. So it's important to know what's the transformation that can have been affected your sediment. One important point also from the economic point of view, it's fluvial sand and gravel are becoming strategic resource. So understanding how they are produced can be important too. So we'll be looking at two parts, mostly the mountain part and the depositional plane, to see if there is some difference of physics and difference of behavior in terms of what's going on the grain side. So let's start on the hill slope, where the sediments are produced. So you know that you can have in the soil and below in the regolates any kind of grain size that goes for clay or close to the soil and organic material to very large boulder. We saw yesterday different processes of physical weathering that can affect your rocks, that makes material that can be granular in size up to large block like here or here where you have some basaltic columns, so any kind of grain size. And obviously, when you go close to the soil, because of the weathering, because of the intense chemical disintegration, then you can get more and more fine sediment. So we go from coarse toward very fine sediments, but we don't know so far what is the granulometric distribution. So there are many studies where people have been measuring in their own landslide deposit the granulometric distribution. So in the following, I will be showing two types of distribution, either cumulative distribution or simple distribution. So here it's a cumulative distribution. It tells you that, so you see there are different lithology, quartzite, schist, gneisses, and it tells you that, for example, the D50 of the deposit of this kind of landslide deposit, in most, for example, for this sample, for this landslide, most of the D50, so the median size, is in between 10 and 100 millimeters, so 1 to 10 centimeters. But the largest size, the D90, can go up to easily a meter. Last information, if we look coarse material and fine material, making a difference or a separation at 1 millimeter. So we have around 90 to 70% of the material of the landslide deposit, which is coarser than 1 millimeter, so coarser than sun size, and the rest smaller and finer than sun size, so 10 to 30% of sun size. So it can appear quite arbitrary to make this difference of 1 millimeter, but it's basically what will be transported in suspended load or partly in suspended load, and what will be transported as a bed load. You can go in different studies. So there is a recent paper by Roda Boluda who did some kind of systematic analysis in Italy and in south of Italy. And she has been looking at different landslide deposits and also making difference between lithology, sandstone, carbonate, gneisses, or even granite. And again, in such a kind of a little less active setting than in the Himalaya, the D50, it's around 20 to 60 millimeter, so slightly finer, but again, a large production of coarse material. In setting still less active, where you begin to have more shallow processes of denudation, so more time to make some soil, more time to make soil, to produce soil. So in that case, you have more time to disaggregate your material. And if you go, for example, here, so this is a paper by Sklar and his co-author in 2017. So they went in San Francisco area, so they are small coastal mountain made of, I don't remember exactly if they are sediments or metamorphic units. And the soil present is quite developed with some kind of granular material. And you see here the mean particle size is below 10 millimeter with a significant portion of sand that can go from 90% sand up to 20% sand, so obviously 10% to 90% of coarse material larger than 1 millimeter. So if we try here,
how to distinguish weather product and landslide material in hill slope process?
Oh,
In the last slide. Yeah. In the field.
There have been what they call weathering product. It's mostly, yeah, I don't know, it's half physical and chemical weathering, and it's just colluvium material which has been sieved, and in this part, the blue one, it's well identified landslide deposit. And here, in fact, the colluvium deposit, so weathered, physically weathered and chemically weathered, it's slightly finer than the landslide deposit. Not so much for the gneiss and schist. You almost produce the same granulometry from the two processes. But here, for the sandstone, for example, the landslide will produce coarser material than the weathering product.
So in one place where both the things are exist, then is it possible to distinguish in the field the weather product and landslide product? Or is this data are taken from a place where only landslide occur and other place where...
No, it's taken the same place.
Well,
same place, the same region, but where they were able to find landslide deposit, they have been sieving the landslide deposit, and on the over hill slope, they took some material at the base, for example, of a small cliff. So at the base of the small cliff, you have some kind of colluvium accumulation of all the small debris that came from rockfall from disaggregation of the small cliff, and all that came down. It's analyzed. So it's, I would say, for the landslide deposit, it's well identified. For the weathering, it's more a mix of different things coming from above. So I cannot tell you because I was not part of the study, so I cannot tell you what's going on exactly in terms of what they have been sampling, but I presume it can be more a mix of different material coming from colluvium process and from disaggregation and small rockfall.
So I guess in landslide place, there also we will find both landslide product as well as weather product, right? In a landslide area, there also we will find both the things together, right?
Oh yeah. I mean, you can even, as I've shown yesterday in the central Nepal, the Kudi area. At the same time, you can find the big landslide. If you move laterally, you can find soil, well-developed soil over 3-5 meters. And if you move to another place, at the base of a small cliff, you can find some colluvial deposit. And if you go on for example, here it's a picture of the Kudi hill slope. So here you have a fracture of the big mass that is collapsing, and you see it's the kind of soil or soil development you can find. Just because before, I mean, when you get this massive collapse, then you get some material coming from above, piling, and here it's just a result of a very complex accumulation. So it's not like the common soil you can find as a common soil sequence. So the organic horizon, then highly weathered, then poorly weathered, then saprolite and saprock. No, already here you get some kind of massive macro colluvium deposit, but that include already some soil and clay from coming from above. Large block will fall apart. So when you go in some basin and you make some hole everywhere, you will find any kind of situation. I mean, you can find normal soil sequence, you can find colluvium accumulation, you can find landslide deposit, and so it's when you go to the field, you have first to identify the object you are sampling. So, for example, a landslide deposit, it's quite, if it's a fresh one, it's quite obvious to decipher from a colluvium deposit or from from other type of
So this one is classified as landslide, or this picture? What do you what we will call this?
I don't know because that's
so can you say that this is landslide because it says angular blocks?
It can be of two origin. I'm not completely sure in this case, because we had 1,000 years ago a large hill slope rotational slide, but unstructure and fracture completely the whole hill slope. So the whole hill slope moved by a few 100 meters, stabilized, and now it's re-incised by the regressive erosion. And so this material can be either during this rotational slide, initial rotational slide, some disturbance, all the upper material which has been disturbed, or the other option, it's just after this disturbance, there were the cliff above of the initial fracture, which was unstable, and large block has been falling, accumulating at the same time that there was some soil development. So I don't know if it's the result. If it is the top part of the initial rock slide, or if it is some kind of mega colluvium accumulation with mega blocks. So I cannot tell you.
Okay. Thank you.
So if we try to get a very synthetic view of what we can get in the different setting. So if you are in a setting where you can have deep-seated landslide, then, so this time it's not cumulative distribution, it's simple distribution. So just to identify the mode, so the D50 will be, we saw between 20 for landslide, 20 millimeter and 100, 200 millimeter. The mode, the rain class, which is the most frequent, will be around 10 centimeter. If you move to, for example, to the San Francisco Bay Area, because of the sediment, because the bedrock is more fracture, and also because it's a less active environment, most of the soil or most of the landscape will be covered by soil and colluvium with a mix of sand, silt, and also a granular material. So in that case, the D50 will be around 2-3 millimeter, and also the mode is around 2-3 millimeter. And if you look at place where you get some large soil development, but even in Himalaya, if you have time to develop some soil, for example, in the crest, then most of the material will be in the granulometry of silt, sand, and sometimes of clay. So you see that already on the hill slope, you have any kind of grain size that you can put in your system. But, for example, in the Himalaya, if we consider that 90% of the erosion is coming from the deep-seated landslide, then we would expect a lot of large clasts, in particular, a lot of material larger than 1 centimeter. Obviously, when you look at the Ganga plain, what do you see? Sun. So the question is, how do we get sun in the plain, and only sun, and what happened to the coarse material? So there are two options. First one, the coarse material had just been deposited upstream, and we get all the sun downstream. And second option, it's we get transformation of the clast by abrasion. So this abrasion, this transformation of the clast from coarse to fine, can occur partly on the hill slope during sediment transfer on the hill slope, because you get some landslide deposit still on the hill slope, and you will be reworking later and weathering and reworking your material. And you can imagine that during this transport of your material down to the channel, you have a first step of disaggregation, or that makes your initial size distribution to slowly get finer. In fact, maybe it does exist, but I'm not aware of a systematic study that's studying what's going on or the grain size evolution along, for example, an hill slope 1 kilometer long. So I don't know if someone has looked really or the efficiency of this abrasion or grain size reduction during hill slope transport. I think that, for example, for landslide, many landslide are reaching directly the river system. So already the material of the landslide deposit you are sieving, it's already almost ready for transport by the river. So I would say that, for example, in active mountain, there is not so much of size reduction on the hill slope, well, from the debris, from the landslide, starting from the landslide deposit material, and most of the thing will be occurring during fluvial transport. So during fluvial, yeah? What is
So what is CWP in the graph? Different graphs which are indicating 0 to 1 values.
I don't remember exactly. I think the W is for weathering. So it's a parameter here. Maybe not. I don't remember exactly. But I think it's a parameter characterizing the intensity of the weathering, or physical weathering, or physical disaggregation. So for a parameter of 0, then it's not modified, and it's hardly reduced in size when you increase this parameter, but it's just a theoretical parameter in the model they are proposing. So, but I don't remember exactly what does it mean.
And in the equation, what is DC? Is it a critical value? A grain size C, and then which is a function of minimum and initial value.
It's the particle size supplied to channel.
DC.
DC.
DC
So
supplied to channel.
So D0 is the initial particle size, and DC is the final size after the slope transform. So, as I was saying, two possibilities to change your granulometry distribution between the hill slope and the basin, to go from dominant coarse material to sun in the plain. We can have particle reduction by wear, abrasion, weathering, fragmentation during fluvial transport, or we can have also selective transport. So we'll see that there is some grain size dependency of the mobility, in particular during fluvial transport. So maybe we can just have left all the large particles in the mountain and just transported the sun down to the foreland basin. This size reduction along the river has been documented for many years and observed in many rivers. One of the first observations was made on the Rhine River in Europe. And after this work by Sternberg, who characterized this decrease of the grain size downward by some exponential decay in some way, with a parameter alpha here, which is a finding exponent. So it's a purely geometric description of the evolution of your load downstream. So for example, in this study, I don't remember which river it is maybe in US, they have been looking at grain size all along the river, and over 40 kilometers they observed some decrease in grain size, and this decrease is characterized by some finding exponent. So we know that there is some finding in many rivers. Maybe we will see not systematic, but it's just a geometric description. It doesn't tell you if it's due to selective sorting of the material or if it is due to abrasion. So let's go to the process that makes the sediment to be transported and to see briefly how grain size is involved. So we know that there are two kinds of transport: suspended load transport and bed load transport. In suspension, so we have basically two forces that maintain the suspension. On one side, you have the submerged weight. It means the weight minus the buoyancy force. That makes that your grains have some tendency to settle down. And because of the turbulence, you have some kind of momentum transfer between the fluid and the particle that will be sustaining or maintaining in suspension your particle. So it's commonly it's describe this suspension by what we call a Roos number. This is a non-dimensional number, which is the ratio of the settling velocity over, I would say, some shear velocity, which is some kind of index of the turbulent intensity. If the shear stress in your river is high, so the shear velocity and the turbulence is high, so the force that the transfer of momentum from the fluid to the grain to maintain in suspension is high. So this part is independent, it's just related to the fluid, independent on the, not dependent on the size of the particle. But in contrast, the settling velocity of your particle is highly dependent on the particle size, and the larger is the size, so the faster the settling velocity, so the faster the Roos number. And so the one who are interested in the how this equation is derived, as you can see in any kind of geomorphology book or hydrology book, and by some simple assumption, it can be shown that on first approximation, the concentration in sediment, in suspended sediment in your water column will be following this kind of flow. So the concentration is depending on the concentration at the base of your, at the top of your bedrock layer, multiplied by a function of the water depth. And the typical shape of this concentration curve is depending on the Roos number. So I made probably, that's fine. So you see that when Roos number is elevated, then there is a lot of concentration close to the bottom and much less concentration of sediment at the top part of your water column. And when the Rose number is low, then you tend to have almost homogeneous or uniform concentration over the water column, just because it's so much turbulent that there is no gradient in terms of concentration possible due to the settling of the particle. So for large particle, because Rose number will be high, will be in this situation, most of the material will be concentrated in the bottom, and for fine particle, it will be mostly uniformly distributed. So we expect the coarse material to travel here, and the flaky and the flaky mineral like mica, and also all the clay and silt, to travel more in the water column uniformly. So it's what we saw yesterday in some way, with a Ganga section with different sampling. I show you these two graphs. So in the basal part, we get mostly quartz and coarse grains. So the bed load is affected by a D50 around 200 micron. And when you go in the upper part, then the coarse material is very rare because it's difficult to maintain it in suspension, and you find only small size material. So we observe some size sorting with depth, and we get a sense that fine material will be traveling on a much longer distance, which is transport in high suspension, and coarse material will have more tendency to be deposited or to travel by small step along the bed load. If you look at the bed load transport, we have three forces: the gravity and buoyancy force. We have some drag and lift force, which is given by the differential motion of water and particle speed. And we have also resistive force of the particle on the bottom. The force acting mostly on low slope channel, well, the gravity component, it's a small null if you have a relatively horizontal channel bed. So the main two forces will be the friction at the base, which is resisting and which favor the immobility of your pebble. And on the other side, you have the drag force, which is the force imposed by the fluid in motion to the particle. And this drag force is depending on one coefficient, CD, of the drag coefficient, and is depending on the square of the relative velocity. So if your pebble is sitting immobile, it means it will be the velocity of the fluid here. And it will be depending on the square of the particle diameter. It seems the section that the pebble is presenting to the flow. The CD coefficient, it's depending on the Reynolds number. In other words, at low velocity, the CD will be high, but in the most river we are concerned with, we get a Reynolds number sufficiently high for CD of the coefficient to be considered as a constant, 0.4, except for the smallest particle for which the Reynolds number will be around those values. So this is a drag force, and if we are interested by the main force of the flow acting on the pebble and on all the pebble on a given surface at the channel bottom, we can divide this force, this total force, by the surface, a unit surface of the channel bottom, and you end up with the fluvial shear stress, which is the force per unit surface made by the river on the channel bottom. So you have this shear force, which will depend, if we integrate over the section of the pebble, which will depend on d square. And on the other side, you have the bottom friction, which is proportional to some friction coefficient and proportional to the pebble, to the stress imposed by which is proportional to the weight. And after of the pebble, after making the ratio of the fluid traction over the bottom friction, which will be depending on, in some way, on the submerged weight, then you will have some kind of expression like that appear. If you make the ratio of the two forces, the tracting force and the resisting force, you end up with some non-dimensional shear stress. So the shear stress we have been speaking about on day first, the fluvial shear stress divided by the difference of density between the sediment and the fluid, the gravity constant, and the size of the pebble. So again, we saw that because of the balance between weight and drag force, it appears that a large pebble will be more difficult to move than a small pebble. Okay? So I've shown you on the first day the bed load transport that makes appear the critical shear stress and the shear stress. So this critical shear stress, we just saw it before, it depends on the pebble size. So basically we have a sediment transport relationship or capacity transport, which is depending in some way on pebble size, but in all kind of bed load transport, it is usually the shear stress is calculated with the median size of your bed load size distribution. We know that in river load we can have any kind of size going from coarse sand to large boulder. So we need more than just this relationship to know how the different particle size are transported. So there are a bunch of studies about sediment transport where people have been looking at how different grain size are transported. So there is no universal relationship, just different result from measurement on the field or experimental measurement, mostly experimental measurement. And it is shown that, well, we could expect, okay, a bigger boulder or a big pebble will have if we have a small pebble, let's say 1 centimeter, and a large pebble 10 centimeter. So here we have the shear stress which is 0. So this one is only defined by hydraulics, by the fluid, and we have here the diameter. So there is a ratio of 10 over the diameter. So we could expect that the shear stress required to, or the shear stress required to move a 10 centimeter pebble will be 10 times higher than to move a 1 centimeter pebble. But in fact, when you look at the critical shear stress needed to move the pebble, so in a extended distribution, so you would expect, if things will be simple, a curve like that. So if you have a grain size of 1 millimeter, you will need a critical shear stress to move it of 1 Pascal. And if you have a grain size of 10 millimeter, you need 10 times more critical shear stress, so 10 Pascal. But in fact, in experimental, in experiment, it is shown that we don't observe that, but we observe rather this kind of behavior. It means that to move a grain size of 10 millimeter, you don't need, if the D50 of your granular distribution or your bed load distribution, if it's the D50, it's 2 millimeter, you don't need a shear stress of 10 Pascal to move the 10 millimeter grain size, just a shear stress of, trivial shear stress of around 2 Pascal. So what is the reason for that? It's just because when you get some distribution of small, big, medium grain size. The large grain size, after some times, so if the small grain size are more mobile, they will be untrained. So after some times, you will have a coarsening of the surface, a coarsening in large pebble, and this large pebble will be much more exposed to the fluid in motion. So the drag force acting on the large pebble will be higher than the average drag force for all the pebble. At reverse, for a small pebble, or even this one, the small pebble will be in the wake of the large pebble. So in some way it will be partly protected from the drag force. So the small pebble will be hidden in some way and more difficult to move that if it will be mixed with grain size of the same as its grain size. So it means that if you look at, for example, a distribution of granulometry going from 1 to 10 millimeter with a median grain size of 2 millimeter, the small grain size will be more difficult to move than if it will be alone, just mixed with other grain size of less than 1 millimeter. And the large particle will be easier to move than if they will be mixed only with pebbles of the same size. So it can be, or it has been proposed to encapsulate this behavior in different equations. One of the most common and simplest one is to consider that the critical shear stress to move a particle is depending on the critical shear stress of the median particle of your bed load distribution, and multiply by this term, where you can see some ratio between the grain size you're looking and the median grain size, so di over d50, to an exponent minus He, the hiding exposure exponent. So for an exponent of 1, so you will get dE for an exponent of 1, you will get dE over d50 over dE. So it will be equal to critical shear stress for your particle of diameter E will be equal to delta rho G, and this one cancel with this one with d50. And what is it? This term multiplied by this term, it will be the critical shear stress to move the median particle. So you see that for an hiding exposure coefficient of 1, you will get the critical fluvial shear stress to move the particle, the coarse particle, the fine particle finer than the D50. You will get exactly the same critical shear stress. So it means that you have equal mobility. So it will be, you don't need extra force, extra fluvial shear stress to move your large pebble. You can move it equally as the median pebble. In contrast, if this term is lower than 1, then the large pebble will become slightly less mobile than the median pebble. It means that in order to achieve the full motion of your large pebble, you will require a little higher shear stress, and for a given shear stress, it means that this particle will be less mobile, less probability to be moved, so more probability to be deposited to get selective transport. So in this paper by Frings et al., which is a review, you can see from field and experiment the different value of the exponent that have been found, and it's between, like here, between 0.3 and 1, with most common value around 0.7. So there is some selective transport, some selective deposition coming from the selective transport, but it's not huge. I mean, if it will be an HE of 0, then yes, the large particle will be much less mobile than the median size. But for an HE of 0.7, you can see that it's not very less mobile, but sufficient to get some selective transport.
So thanks. I mean, yeah, this is an interesting data set. But looking forward for this area of the drag force, and will it not be good to use the D90 rather than D50? Because the D90 is the representative size of the biggest class, and that will give an idea that the drag force has enhanced in the system, and the selective transport will be more about that what is the course's size which was moving. That's the one thing. Second question then, is it based on the flume experiment where the density was same for all the grains, or density was variable? So omega value
I'm not
same.
completely sure. I don't know enough all the literature on the subject. I would say that over 90% of the bed load transport capacity relation are using D50. So I don't know if some relation use D90.
Okay, because some of the literature, so not in this equation, but some of the literature use D90 to define the transporting capacity of the system, because that's the representative of the largest class.
Yeah.
And now with this definition, when the finer grains have removed and more area is available for drag force, then in this case, because in this figure, this grain is representing the largest class, not the average class.
Yeah.
And if we put the larger class around that thing, then that explanation will be more valid for the D90 rather than D50.
Well, maybe in the stream mountain, maybe it's becoming crucial to. It can be crucial to use a D90, because in a mountain stream you have very large extended granulometric distribution from sun to border, which are several meters. So maybe in that case, in most alluvial river, because people consider that the grain size distribution is less extended, in some cases, there have been documented the equal mobility. So it's, for example, a paper by the work by Parker and Klingerman. So equal mobility, it means that you will get some HE close to 1 and equal mobility of any size. And as far as I remember, equal mobility has been documented for grain size distribution, not too much extended. And if you get several order of magnitude between the finest and the largest class, yeah, maybe the issue of the D90 is becoming more crucial. But I cannot answer you because most of the transport capacity ration that people use is accounting for D50. I don't know so much ration that use D90. And at least for this bedload capacity, but maybe just to know when you, I mean, by this effect, you can also, by the winnowing effect of the small particle by the large one, you can also explain some feature which is observed in many rivers, which is the coarsening of the upper of the surface layer, or what we call the pavement. So usually the surface layer is coarser than the sublayer in your alluvial deposit. So maybe when you want to have some large bedload transport, you need first to break this pavement or this surface layer, and to break or put it in motion, maybe the D90 is important to take into consideration. But I'm not sure of the different expression, and I'm not even sure what people will consider. Will it be the D90 of the distribution of the surface layer, or will it be the D90 of the sublayer? I don't know. Yeah.
Yeah, the surface D50 and the subsurface D50, they are plotted separately.
Yeah, but it's a very it's not a very coarse material. It's between 1 and 10 millimeter. It's yeah.
Okay.
So whatever we consider transport by suspension or transport by bed load, we expect in the two cases, for suspension it's obvious some strong effect of the grain size. For bed load transport, there is more variation between over the exponent that makes some cases the selective sorting is not so important, but in some other case we can expect the bedload transport to produce some selective sorting, some selective transport. So it can be a very efficient way to modify the grain size downstream. Large class are less mobile, small class or small particles are more mobile, so you would expect to deposit the large class in the upstream part and to move only the small particle. The only problem, so we could explain the finding, the downstream finding, just by selective sorting, but the only problem is to get sorting, you need selective sedimentation, you need sedimentation. So you need to have some space or some place where you have permanent aggradation to make some sequestration or storage of the large pebble. In a mountain range, there are valleys, sometimes there are terraces, so we know that there is some temporary storage. But on the long term, the terraces will be re-incised, re-eroded, and all the material will be evacuated from the mountain range. So there is no long-term storage possible in the mountain, so we expect that anyway, all the material will be transported downstream. So in that case, it's difficult to imagine that you can just have some finding by selective sorting. You need to have an extra process, and it's most probably the abrasion to find your sediment. So let's let's see now at the abrasion process that can reduce the size of your particle. And for that, I will show you some example from central Nepal. We studied with a former student, Mikhail Attal, several years ago. Go back to central Nepal, the Narayani watershed. Here at the middle, the Marsyandi River. And we sample gravel bar all along this river. So the river is starting, or headwater is in the Tethesian series, draining mostly carbonate units, arriving in the gorge of the High Himalaya, draining gneisses, and then draining lesser Himalayan units, mostly sandstone, schist, and quartzite. So we're interested in finding. So let's have a look at least the gravel size and the gravel distribution all along the river. So to document the gravel size, so very basic, we go to gravel bars at low flow. It's a proxy for transported bed load. We have been also documenting the potential source, the moraine, the terraces, and mostly the landslide deposit. And we did Institut granulometry for the large class, larger than 1 centimeter, and also some analysis in the lab for the smallest fractions, so large, smaller than 1 centimeter. Two techniques. For the surface layer, for the subsurface layer, we made some sieving and weight counting. So it's quite exhausting method, because normally you have to consider some volume of material you are going to sieve in proportion of the largest class. So if the largest class is around like 40 centimeter, you should take tons of material. So in our case, it was not possible. So there is always the possibility of some kind of bias, the fact that you cannot account for the largest class. But anyway, it's sometimes you have no choice, or because it's too difficult in such environment to sieve tons of material. For surface material, the surface of the gravel bar, classical technique, point counting, as
Excuse
Raoul.
me, Jérôme. How much depth you dig for the particle size analysis here?
How?
In the field, how much depth you are digging?
It's just a matter to remove the surface layer. So if at the surface layer the D90 is, for example, 30 centimeter, then you have to remove more or less 20-30 centimeter, and then you can take any material from below this surface layer.
Okay.
So you don't need to go very deep. You just have to remove the surface layer.
Okay.
So then for the surface, you can not do some weight counting. You need to do some point counting. And it can be done either with a tape measure on the field, or it can be by just taking a picture and counting the pebble size. So you can do it manually on some kind of grid on your laptop. And now there are also more and more people trying to make some automatic recognition of the shape to extract the grain size distribution. So in particular, one of the next Bodo Kagan will be giving class on next week, has recently produced some automatic software to extract pebble size. Well, I don't come back on this. Characterization of the sources, terrace, moraine, and mostly landslide. So we get initial value between 30 and 60 millimeter. And then we look at the gravel size of the bar, and surprise, where we will have expected some downstream decrease from upstream to downstream. We were more looking at some kind of increase or constant or uniform grain size. So here it's STD, it's above STD, it's Tibetan series, carbonates. Between STD and MCT, the gneisses of the high Himalaya, and below MCT, mostly lesser Himalayan unit, down to the mountain front. Whatever you look at subsurface or surface, obviously surface layer is coarser, between 10-15 centimeter, it's coarser than sublayer, around 8-10 centimeter. But in both cases, we saw some kind of uniform or slightly increasing size of the increase of the median size. I just added this plot here to show, maybe you cannot read. So we did some comparison between the point counting on picture, on photo, and tape measurement on the field. On average, there is a relatively good match, except that in general, the picture of the point counting on photo, in some case, underestimate the pebble size, just because when you take a picture, maybe you will be missing the largest pebble. When you do the point counting with a tape meter, which is 20 or 50 meter long, there is more probability to hit a large boulder. But otherwise, if we accept this kind of bias, that's, we get relatively similar results. But anyway, the most important thing is we don't observe this decrease. When you look at the literature, you can see plenty of study about grain size evolution. So many of them document whether it is in gravels or it is in sand, some finding downstream. But a few of them, in particular in active setting, in active mountain setting. So again, this is a peninsula of the Olympic mountain I've been presenting over days. And you see in the clear water drainage, people have been working on the grain size, looking at the grain size from upstream to downstream, and you see here uniform grain size. Well, in fact, finding uniform grain size, it's not so surprising, because let's consider a pebble. So a pebble will go downstream, and if it is abraded, it will lose some material. So we'll saw, if we consider that, like, if we consider that, maybe the decrease in size or the decrease in mass or in volume is something which depends just on the travel distance. So you get d over d equal minus k dx. So you get d0, this explanation of the exponential decay. So here you are just assuming that the loss of mass or the loss of diameter by abrasion is just a function of the travel distance and on the initial, on the diameter at some given moment. So you would expect from this equation some exponential decrease of your diameter when you go downstream, as in some way proposed by Sternberg law. This is for one individual particle. But if you consider that if you are in an active setting mountain, so this is a fluvial network, Okay, you have one pebble here traveling that way. And when it arrives here, it is smaller because of the abrasion. But if your basin is eroded at uniform rate, you're putting also pebble from here and pebble coming from here. So at the end, this one is traveling much less, so it's still quite big. And when you look at the median size, because this one has lost a lot of volume in your grain size distribution, it doesn't count so much. So when you integrate over the whole basin all the grain size coming from different location, then you can show that theoretically, if you have just this kind of relation of exponential decrease with the distance, then if you put regularly material into the system, instead of having for the whole distribution of your sediments, instead of having some exponential decrease, you can show that you tend to somewhat to some kind of asymptote, which is around 70% of the initial size. So instead of having some constant decrease, you will have some kind of uniform evolution. So obviously, this evolution will depend on the coefficient of abrasion. If your lithology is highly erodible, so very quickly you will reach this uniform behavior. If it's very resistant to abrasion, then it will take more distance to reach this, this plateau. So again, this plateau of this behavior is due to the fact that you are adding constantly fresh large pebble, and based also on the fact that the one that came from far away, they have been so weird, so abraded, that in terms of volume, the contribution to the distribution is very small. So when you look at the diameter, obviously, you don't see an effect of the abrasion, but if you have access to the sediment flux, obviously, if you look at the bed load proportion, because of the abrasion, then it will drop with distance, because you abrade quite a lot the material from here, also the material from here, a little less from here, but in total, all the abrasion of this material will produce a strong reduction in the bed load. So if you look at the flux of bed load, the total flux, you have a drastic reduction with the distance traveled. If you look just at the pebble size, you don't expect so much reduction and even some kind of uniform uniform size. Oh, sorry. So it seems that the pebble size, or the finding of the pebble size, it's not very relevant in active mountain to really document or to reflect the abrasion process. So if we want to see the bed load evolution due to abrasion, if we want to find some way to evidence the abrasion of the bed load on the field, then we need to look at some other effect or other variable. Imagine that you have in your basin 3 distinct lithology. One easily erodible, one medium resistance, and one very resistant. So if you look at the proportion of these different lithology, so the one which is poorly resistant will be eroded or abraded quite rapidly, and its proportion in the bed load will drop to almost 0. In contrast, the highly resistant material will tend to be dominant in the bed load. So the highly erodible material will disappear, just disintegrate by abrasion, and will be transferred to suspended load, the coarse material, the resistant material will be more and more dominant in your bed load, because the pebbles of the resistant material will be preserved during the transport downstream. So if we look at proportion, lithologic proportion along the river on the gravel bar, maybe we can get some information about the abrasion and about the relative abrasion of our pebbles. So this is the lithologic result of the lithologic data. So when we are in the Tethys series, it's mostly carbonate with a little of, I didn't put the legend, sorry. So with a little of sandstone. Here, the pink, it's the gneisses, sandstone and mostly quartzite for the yellow, carbonate for the blue, schist for the green. And you see that even there are schists along the drainage, along the watershed, we don't find so much in the gravels of the bar, maybe because we are not so much produced in coarse fraction on the hill slope, or maybe because they are fastly destroyed during river transport. We saw a large proportion of gneisses, but we saw that when we arrive in the Narayani River, the proportion of gneisses has dropped significantly to less than 20%, and most of the pebbles are made of quartzite. So in order to try to understand the abrasion process and how it will split the different lithology, maybe we need to know first what is the erodibility of the different lithology. So one way to know that is to run into an experiment to see how the different lithology are abrading. So this is the film I will speaking a little more later. And you can see the different Himalayan lithology going from quartzite to schist. So the quartzite are quite resistant, so they are losing mass 0.1% of the mass per traveled distance, per kilometer or traveled distance. So after 10 kilometers, you will have lost 1%, and after 100 kilometers, you will have lost 10% of your mass, so almost no size reduction. In contrast, for example, for schist, you see, after only 1 kilometer of fluvial transport, you already lost 10% of your mass. So 2 orders of magnitude difference in terms of lithology between quartzite, schist, with the gneiss and the carbonates at intermediate value. Yeah. It's, I mean, I don't remember exactly what we put in this data report, but well, for sandstone, you can have any kind of sandstone. You can have very poorly cemented and almost quartzitic sandstone, so it's not a surprise. For granites, depending on the size of the crystals and also on the initial state of the granite, if it's slightly weathered, it will have tendency to wear more rapidly. And you can see quite a difference for the gneisses. It will be depending mostly on the content in mica. So if it's very mica biotic rich gneisses, you will be somewhere here. If it's quartzitic gneisses, or if it's there is a formation called F2 in the high Himalaya that correspond to the calc gneisses. So gneisses rich in poor in mica and rich in poor in quartz, also, and rich in diopside, and rich in there is a little of calcite and a lot of feldspar. And because of probably of the absence of biotites and mica, it makes them quite more resistant than the biotic rich gneisses. So obviously, for a given lithology, we don't have just a single value, it's some extended value. But we can consider some average behavior for each lithology. Yeah?
So this is like mass loss per kilometer for different rocks.
Yeah.
So limestone is loss of limestone is what it is losing more.
Yeah.
Achha.
More than what? It is losing more than quartzite, but is losing less than schist, for example.
Achha. And what is this star mark here?
The star? It is just the average value that will be used in the model in the following slides.
Okay.
Okay, so if we want, we get the experimental erodability, and we can be interested to see what's going on when we put all the material with different erodability into the system, and what's going on downstream. So you can calculate the distribution of your pebble size along the river by integrating over the watershed, and to integrate the quantity of the different lithology, you need to have some erosion map. Obviously, if in that part the erosion rate is higher than here, then you will get more material coming from here than from the low erosion part. So you need to have some erosion map, so it can be based, for example, on the shear stress map, or it can be based on the cosmogenic nuclei or whatever. You need also to know the initial distribution of the material coming from the hill slope. So let's take the distribution coming from the landslide. And you need to know for each lithology the erodability factor and also the local proportion. So here it's 100% gneisses. For the red one, 100% of granite. But in the green units, it's a mix, maybe 10% quartzite, 80% or 60% sandstone, and 30% schist. So it's according to the lithologic description of the different geologic units. You can more or less estimate the quantity of the different lithologic unit. No, it's just a budget. Yeah. So this is the case empirical. The initial distribution, it's field measurement. And obviously for the erosion map, either you take some kind of theoretical, a virtual one based on the shear stress measurement, for example, or you have some good idea of the erosion rate because you get some barium 10 measurement in your different basin. Sorry?
This initial distribution that we are talking about, where should we measure it? Like just at the start of the channels, and then?
In theory, in a perfect world, you should go close to the channel, put some kind of huge sediment trap, wait many years to see what you get, and take this material. But it's not possible. So it's either you consider that, for example, your dominant process is landslide, so you measure gravel size in landslide and make some average distribution, or if you consider that the dominant process is shallow landslides, superficial erosion over 20 centimeter maximum 1 meter, and you go on the field and you measure the size distribution of your soil column over 1 meter, or the colluvium package if the colluvium material is the dominant material going to your channel network. So depending on what is the dominant hill slope process, measure the product of this dominant hill slope process.
Thank you.
But yeah, it is a strong assumption. It means it's probably, maybe it's the part where there is more uncertainty because there is so diversity on the field between place to place and even between landslide. And even within the landslide, if you look at within the material within the landslide, between the top of the landslide deposit and the bottom of the landslide deposit, you can have some significant variation in terms of grain size. Usually, during granular flow, there is a tendency to have coarser material at the front and at the top of the debris deposit.
Jérôme, you wrote there steady state model of pebble abrasion. What is the meaning of it, of steady state model of pebble abrasion?
Steady state, it means that we will considering that any kind of sediments that come from here is transported to here. And at steady state, it means that it's uniformly eroded here and coming here. So that way, the sediments you are considering here, you don't care about time. Otherwise, if it's a transient state, then you will have to account for the traveling time. So it means the gravels you are measuring here, many gravels, if it's coming from here, it took maybe, let's say, 2 years to go from here to here, from the tributary here to here, and maybe it took 10 or 20 years or 50 years for a pebble from here to go from here to here. So if it's not at steady state, you will need to worry about the time to transport your pebble from here to here. But if it's at steady state or it's constantly providing at the same rate with the same quantity, with the same grain size distribution material in the different part of the watershed, then you don't care. You can do this kind of calculation.
All particles have same rate of transportation. All pebbles.
Here we don't care, because whatever it takes 100 years or 1 year to go from here to here, the particle that travel that went in the drainage network 100 years ago, or the one that come here last year, they have all the same characteristic, and they will be traveling with the same flux up to here. But if we look at some transient feature, or also if we have some temporary storing due to terrace formation, in that case, this kind of equation is no more valid, and you have to go into more complexity, introducing time. So again, the data, the observation, gneiss.
Jérôme, we can have a tea break because.
Okay, maybe let me finish that part.
Yeah, okay.
Gneiss and granite in pink, limestone in blue, and schist in green, quartzite in yellow. The data, just the model if you consider that there is no erosion. So in fact, no abrasion, I mean. So it's representative, this proportion, of the different proportion of lithology in the basin. So you just consider the proportion of lithology, and you consider, and you expect, in that case, that all this lithology will be represented equally in the bed load. Because of the erosion of the sedimentary series, you have large quantity of limestone. You expect also significant quantity of schist, and obviously gneiss is coming from the high Himalaya. And quartzite, true quartzite, is not so common, like less than 10%. If you consider the erodability, the lower erodability for quartzite and much higher for schist, it's, you take those values, it's what you obtain. So the limestone are decreasing quite fastly. The schists, they almost doesn't appear because they, as soon as they are transported, they are reduced in size. Gneiss also are reduced, but they are dominant over schist and limestone. And you see the quartzite, normally you would expect 5%, and here you get 30 to 40%. And obviously, if you put slightly different value, in particular, if you take larger value of abrasion rate, then you will get such the effect of preserving the most resistant pebble, for example, the quartzite, it will be much more prevalent. So what we observe, it seems that this 50 to 60% of the distribution made of quartzite in the Narayani, it's just the expression of the fact that the quartzite is much more resistant to abrasion than the other units. And you see, taking the experimental value, we are almost able to reproduce what we observe in the data. And without abrasion, it's not possible to reproduce the observation. Okay. Yeah?
So in this diagram of the relative lithologic proportion, so the previous one, if you could please go back. So this was, if we see across the strike of the Himalaya from the Tethys to the to the Narayani river. So I think you made the inference that the data relates that the quartzite is more resistant to abrasion.
In here and here, in these two models.
So I was looking at the drainage map, like in this area. So could another inference also be made if we see in your lesser Himalayan block, there are less antecedent streams and more linear drainages. So your contribution for quartzites is coming majority from the lesser Himalaya, and not and to as you go to the Narayani basin. So can that inference not be made? Because if we see the Kali Gandak river also, it has an eastward deflection before it's coming. So even drainage can have an effect on this. So, so I think you've understood.
You mean, I mean, obviously, and it is already included here. I didn't mention it, but using, for example, ArcGIS and the flow accumulation, then you can derive flow length. So for each, I computed the drainage network, and for each little g, for this one, I calculate the distance that the gravels of the particulars to travel, and I consider it in the abrasion term. Okay. So a pebble coming from here, anyway, it has the same erodability as this one. This one will be more abraded than this one, obviously, because it has to travel a longer distance. So distance, yeah, the fact that the quartzite are closer from the outlet has some impact.
So I think you have some data from fluvial terraces also. So those must be on the Narayani, so that watershed would increase, no? Or all the data is within this watershed?
All the data is looking at gravel bars, yeah?
Within the irregular polygon that you have drawn, all the sampling points are within this, or?
Sorry.
So the sampling points, so if for the HFT, they will take into corporation a bigger drainage, no?
Yeah.
So I was just interested, I just thought of that you have a lot of longitudinal linear drainage concentrated in your lesser Himalayan sequence in this region. So could that also be an inference why you have more quartzites in this in the data?
Normally no, because I mean, whatever the shape of the drainage, and in any case, if, for example, at Narayan-Ghat, so you are below the confluence between the Marsyandi and Trizuli and the Kaligandaki, and the Kaligandaki has made a long travel in units of the lesser Himalayan units, sandstone, quartzite,
It's
dolomite,
taken a eastward
but
deflection.
this contribution, well, according to the erosion map, when we arrive in that part, this contribution by the flow integration is already included. I mean, the fact that we are traveling over long distance in the Lesser Himalaya. So I'm not sure to understand your question. If it's a matter of sinuosity or shape of the drainage network, it doesn't matter so much.
So that will influence the transport
The sinuosity?
the transport distance. Yes, sir.
Yeah, the sinuosity, but so if I don't remember which DM we were using.
So not about DM. Even if you see it has taken an eastward deflection.
Yeah.
So I thought you could have longer transport within the quartzites of your lesser Himalaya. So that will influence the final model where we have more quartzites towards the fall end.
Normally not. I mean, for example, for the Galigandaki, so it's sinuous, it's deflected, so there is a long transport here. So obviously, it will have, yes, it will have some effect on the preservation of quartzite, because not because you are draining the quartzite here, but just because you increase the distance of transport. So by increasing the distance of transport, if there is some difference of erodability, you will increase the effect of the relative difference of erodability. So if you travel over 10 kilometers, then you have not so much time to differentiate gneisses and quartzite. If you travel over a distance of 300 kilometers, because it's a long way and it's sinuous, yeah, you will get more and more abrasion. Obviously, the less resistant lithology will be more abraded or more affected by the long distance transport. So the main effect of the channel network, it's not the fact it's draining the lesser Himalaya, it's more or less a question of lengthening the total distance of transport. So magnifying the effect of the differential abrasion.
Thank you, sir.
Jérôme?
Yeah?
So in this paper, so you have three classes, I think, three classes of gravels.
No, it's, we look at well, basically we look at the full distribution of the gravels.
Full distribution of, for quartzite, you have considered pebbles of, like whatever you have selected, the minimum size, let's say 1 centimeter, from 1 centimeter size to 6 centimeter size. You have considered for all, the abrasion rate or erosion rate.
Oh, no, the only things, I'm trying to remember. The only thing we were considering, it's on the field, when we have been doing tape meter counting or sieving, it was not possible to look at the lithology of very fine gravels because it will take too much time. So we have been considering only the pebbles larger than 4 centimeters for the lithologic counting. But above 4 centimeters, it's if we have a block of a pebble of 30 centimeters or 10 or 8, we all look at the lithology of the pebbles above 4 centimeters.
So size and shape are they are also two important factors when we calculate this erosion rate. This should be, because larger is the size, the faster will be the erosion rate, size of any gravel.
Well, it's not so.
And shape is also one of the factors. Like
It's not so easy to answer this question because in nature, well, in the experiment, all the pebbles are moving at the same rate, so at the same velocity. So we get some kind of abrasion value. But this abrasion value, it's not directly the true abrasion value in the nature for many reasons. Because in fact, the abrasion rate or even in experiment will be depending on the size, but it will be depending also on the pebble velocity. And it's quite dependent on the pebble velocity. So, but in a natural stream, you don't know exactly. I mean, during a low flow or a medium-sized discharge, maybe you will be having your bedload traveling at low velocity, and during high flow, it will be traveling at high velocity. So in theory, it will be necessary to integrate of the flow distribution and to account for a coefficient that depends also on the flow transport. But it's first, it will be necessary to have a good relationship for k in function of velocity. And another factor, it's for the large clast, if because they are less mobile, or in some way slightly less mobile than the smallest clast, sometimes they can just stay at the middle of stream and they will be hit by this, the smaller pebble size. And it will change also, it will increase the apparent erodibility of the largest class. So in fact, we'll need to account for many effects, both relative to discharge and relative to pebble size, but we don't have for the moment all the physical relation and even the discharge history to do this kind of work. So it's just a first order view by taking a constant parameter k that just depend on lithology and do not depend on transport stage, pebble velocity, diameter, whatever. It's a simplification. Models are simplification in general. Otherwise, you cannot encapsulate all the complexity of nature. So, abrasion is seems to be an important process that can explain the lithologic variation. But so far, I just spoke about the abrasion of the pebble, and I don't say what's going on for the residue of the abrasion. So we can see at the fragment of abrasion. So we can have, during the size reduction by abrasion, two types of process. Either fragmentation, that will give you, by splitting several pieces from the initial pebble, or you will get also very fine fragment in silt and sandstone, which are the product of the abrasion just at the surface, the wear of the pebble. If we look at the quantity of fragment over fragment production rate over attrition rate, you see experimentally that if you have large particle and if you have large velocity or pebble impact, there is more probability to get fragmentation, and so the ratio of fragmentation over attrition or wear rate will be higher. So obviously, this transformation process depends on diameter, depends on velocity, and otherwise, if we look just at the attrition product, so we will get mostly depending on the lithology. So for this one, I think it's for gneiss or limestone, I don't remember exactly, but typically you will see good part of this attrition product in the silt and sand. Well, obviously, you can get also some fragment. So when you get some erosion, abrasion of your pebble, you will produce small fragments, small chips, and mostly sand and silt. And this sand and silt, I mean, the fragment will be keep on traveling with the bed load, and the silt and sand will be traveling mostly with a suspended load. And they can travel far away. Sorry? Micro? It's okay?
Jérôme, can you go back to your previous slide? Yeah, here it's a density plot, right?
Oh, density, it's a density function. Sorry. Just a distribution.
Okay, so maximum density lies in silt range, silt
So
percent.
this is a density function
Oh,
or PDF. So the mode is around 0.03, 0.04 millimeter. So 40 micron for the largest proportion of the product of attrition.
okay. Oh, okay. I thought that it is density. So
No. Because the size gap, it's in the, this is the distribution of the abrasion product, okay? So because there are basically two different processes, fragmentation and wear or attrition, surface attrition, we see the signature of these two processes. The fragmentation give coarse fragments, the attrition fine fragment, and in between there is no process that contributes significantly to produce particle or fragments in the size 1 to 10 millimeter. In the distribution, yeah. So we start with some initial distribution from the landslide with pebbles, with particle, a mode around 100 millimeter, and by abrasion, we will transform viscous material in slightly finer fragment material, and of course, a large proportion of attrition product in silt and sand size. So as a consequence of that, so when we go downstream, I'm trying to remember. When we go downstream, we have more and more abrasion product that go into suspension. So from the beginning, we have mostly coarse sediment, and at the end, we have mostly suspension material, with a lot of sand also, and little less bed load. And second things, it's you start, for example, equal quantity of low erodibility in orange and high erodibility in green. And after some transport, obviously, if you have more pebble, more resistant pebble in the bed load, in the suspension load, you will have a larger proportion of material coming from the high erodibility material. And it's more or less what we observe when we look at the limestone proportion. So in blue, this is a bed load. So the star corresponds to the measurement of the bed load, and this line corresponds to the model I presented previously. If we look at the bed load, so a large decrease in proportion of limestone. In contrast, if you look at suspended load, so unfortunately we had only two points of measurement, one here and one here, and we see that we got like 20% calcite in the suspended load. And for the sand is in between these two values. So depletion of carbonate in the bed load because it's more erodible and because it's traveling from a longer distance. And enrichment of the suspended load in carbonate because it is a product of the abrasion. Okay, so pre-conclusion for that part. No transcription of the individual abrasion of individual abrasion. If you just look at the size evolution downstream, the mean size evolution on gravel bar. So to evidence the abrasion, it's easier to look at the lithologic proportion evolution. And with the potential effect on suspended load, lithologic content I was mentioning. When the load is arriving in the foreland basin, what's going on? So in that part, we say we expect mostly abrasion, and indeed, with a simple model, we can more or less represent the main feature of this evolution. In that part, we expect, because there is some permanent storage, some permanent sediment sequestration, we expect the selective sorting to be much more efficient. Because here, if you have subsidence and permanent sequestration, so you will have, it will be much easier to deposit the large class than the fine class for the reason I gave earlier. So let's have a look at different rivers in the Piedmont, in the foreland basin. So I will show you first some, mostly some results along small river. The advantage of the small river is because during winter time there is no water, so it's easy to go there and to make some sieving after weighing. And you can see, for example, here for this small river draining the seawalix and then arriving in the foreland. But here in the seawalix we have gravel mostly transported in the channel. And when we arrive further downstream, there is just sand. So how is the transition? In fact, the transition is quite abrupt. So over 10 kilometers from here to here, it's almost gravel, slightly decreasing, but not so much. Both the D10, the D50, so the median size, and the largest class, D90. So it remains slightly constant, slightly decreasing, and then abruptly it's dropped by 2 orders of magnitude, and we arrive in some location when there is where there is only sand transported. So we get some large grain sand transition, and if we look not only at D50 and D10 and D90, but at the full distribution, you see again the bimodal distribution we have between the bed load gravels and the sand. We go downstream. Here we begin to have a strong reduction in the mode of gravels, and then after this gravel sand transition, then this gravel mode has completely disappeared, and we get only the mode of the sand and the silt. We have a direct transcription of this grain size evolution here if we look at the slope, or if we look also at the profile. So this is the profile, and this is the channel slope. And you see that after the gravel sand transition, there is a strong decrease in slope, and even during, in between the outlet of the range and the gravel sand transition, there is some decrease, clear decrease in the channel slope. We can move to other rivers, like the Ratu River, which is further east, and same. We leave the mountain front, and then there is a drop in channel slope, a significant drop after the grain size gravel sand transition, and again a decrease. What does it indicate? It just indicates that you get some sedimentation and selective transport. Sedimentation makes that the sediment flux is reduced because you are storing sediments, or part of the sediment load will be deposited, so when you go further downstream, the net sediment flux is decreasing. So if you have less load to transport, the river don't need so much, so steep slope to transport this reduced flux. So for that reason, we see this decrease. And because after the gravel-sand transition, then you have no more gravel to transport. Transporting sand partly in suspension is still easier, so you have another reduction of the slope, because the river doesn't need to have very high slope to transport a reduced sediment flux with reduced size, grain size. So a very efficient selective transport and sediment sequestration over 15 kilometers. Colleagues from Scotland have been doing the same kind of measurement along large river, Yamuna, Ganga, Karnali, Gandak, and Kosi.
Zero.
Yeah?
Can you go to your previous slide? Yes. So here you are saying that the slope transition is the main factor for the grain size variation transition.
No, it's a reverse.
Yeah, it's
a gravel or the load evolution in terms of flux and size that determine the slope.
yeah, but it can be other way around. At the foothill, maybe we can have a high, means larger particle, because slope is high, so most of the particle can drag with that slope, and we can have a larger grain size at the foothill of that slope. Means there we can have a.
I'm not sure to follow you. I mean, here, well, for example, for this
Yeah,
small river, most of the load is coming from the conglomerate of the upper Geochimiques. Okay, so the river is transporting the product of erosion of the Geochimiques conglomerate. When it arrives here, I mean, there is no contribution from the front because it's not very steep, and the river is flowing that direction and is depositing gravels, the coarsest fraction. There is still remaining gravels, so it's depositing more gravel, and when it arrives at the sand gravel transition, there is no more gravel to transport, so it just transports sand.
So basically at the base of the slope, where the slope transition take place, there we can have a high grain size particle deposited for a.
You mean here?
Means
or here?
whenever we have a means slope transition, means higher to lower,
like here and here, or here and here.
Yeah, change in gradient. At the change in the gradient, that transition can be marked by the higher pebble size grains. Could be possible?
I understand more or less what you mean. If, for example, you look at some flume or some artificial structure, obviously the initial condition will be dramatically impacting the kind of material you are depositing. So if, for example, you have high slope here and you arrive in a zone with a low slope, then you will have tendency to deposit all your coarse load in that area, and not here. So this is true, to my mind, this is true when you impose a system because you are building some concrete channel. But here, the system is free to evolve. So it's not the slope which is imposed and which will force or impact the gravel deposition, but it is a reverse. It is because of the condition, because of the deposition and the reduction in flux and size of the gravel, then the channel will adapt its slope to the transporting condition necessary to transport the load coming from upstream. So there is some kind of imbalance or a coupling between the load and the slope, but it's mostly the quantity of slope, the quantity of sediment and the initial size of the sediment that will influence the slope evolution if the system is free to evolve by itself.
So basically, same question. So here we have two things. Now, slope controlling transport process, and then the reverse is sediments or the whatever size classes that has been provided to river that controls the slope. So, so there are two things now here. One is slope that controls the gravel size, which has to be transported. Second is the sizes, they control the slope. They they impose the slope condition.
But it's mostly size and quantity of sediment to transport that impose the
Yes.
slope.
So here in this particular case, in the mountain section, naturally the topography is such, and there is uplift, there is other things because of which river has to adapt to a higher slope rate. But once it comes to plain, there is no uplift and topography is as such flat. So even if we supply it with large amount of sediment, it won't adapt to a higher gradient state, because then topography is already flat. It cannot incise as such.
No, because it's again, I mean, the sediment flux is dictating the slope, because if it's a long-term process, you have to think in terms of geologic time scale. Let's say you have a flat surface and a steep gradient with the MFT, and you are bringing a lot of material. Okay, you say you have this slope. So what happens if you have a flat slope and you are not able to transport this large flux of sediment? You will deposit it. Then there is still not enough slope to transport all those sediment. Okay, make more deposition. And then you will create by this way. So there is some activity, some erosion. So slowly and slowly, we don't care about that part. But after some times, if the river is fed by a certain amount of sediment flux, it will adapt by just aggrading. It will adapt its slope in order to be able to transport all these sediments. And if at the same time you have subsidence, so there is some sequestration. So after some times, because the QS, there is some part which is sequestrated, QS is decreasing downstream. So you don't need any more large slope to transport your sediment downstream. So you will see something like that. And then you are not going to keep a tunnel A. As soon as this slope is sufficient to transport this flux, then you will get, you can reach some kind of steady profile. So yeah, I agree that at the beginning, if you are some initial condition that you impose to the system in terms of profile, then the profile is dictating what's going on in terms of sedimentation. But once the system is arriving at steady state, this is the sediment flux arriving from upstream, which is dictating the final shape of the profile. You understand the difference?
Still there is a little bit of confusion, because ultimately what GST is a point where there is a transition, sudden transition.
Yeah.
So in the previous graph also there is size class difference where there is distinct bimodal distribution sort of thing. You have sand classes and then you have gravel classes.
Yeah.
So, so naturally, river has the material that it needs. Now there is something because of which it is not being able to carry those things further downstream. Now, when we calculate whatever stream power or shear stress, we always take slope as contributing factor, and slight change in slope like from 2% to 1% changes, even though in field it is not that much great, but in the equation, that is again, that can bring a 100% change in stream power. So that's why I was emphasizing on that particular thing. And then the rivers that you have shown here. So in most of the cases, we find this gravel sand transition uh, at a range of almost 12 to 16 kilometers downstream of MFT. So sort of that is relatively constant. And even if we follow the Dingle-et paper, there also that transition varies between 20 to 40 kilometers, whether that is Kosi or Ganga. So irrespective of any size, irrespective of the basin area or type of lithologies they are coming from, so ultimately they are limited to maximum downstream distance of 40 kilometers. So, so therefore, I was under the impression that topography must have some control on this, whether that is because of subsidence or because of the slope change. Topography should have some role, since you know, change the basin area, change lithology, change any supply, do whatever you want to do, but then ultimately that GST distance from MFT is sort of fixed, 15 to 40 kilometers.
I agree that at first glance it can be slightly puzzling, and I don't have a definitive explanation. I would be more cautious than you about the fact that the gravel sand transition is always at between 10 and 15.
Small rivers.
It's well, if you take a small river draining, for example, mostly sand units, the middle, then the sand transition, it's gravel sand transition, it's in 1 kilometer you can observe it because there is almost no gravels. But you are true that in the fact that the maximum, I don't remember, maybe it was for the Bagmati of the Bakia River, the maximum distance is around 20 kilometers, and all the time it's in between 10 and 20. But if you look, sorry? And if you look at this study by Dingle and co-author, they still observe some difference between the COSI and, for example, the Sharda, where there is a difference of that goes from 40 kilometer and 10 kilometer. I don't remember exactly. I don't remember if it is in this paper or in another one, but we are proposing that there is a difference of subsidence rate between west and east, and where you have more subsidence here, you get more sequestration, so more quickly you get the gravel sand transition, and where you get less subsidence, so less sedimentation, then it takes more times, more distance to empty or to remove all the gravel of your systems. So that will explain the larger distance. But yeah, I don't have explanation why it's there is such a regularity. I mean, between 10 and 20 kilometers, we could expect slightly more variation. It's a possibility.
We have 7 rivers. They are draining in Han salient, and GST you will find at varying like distance from MFT. There are rivers which are originating within middle Sivalics. You will find GST just like decreasing within a half kilometer. And the rivers which are larger size around 120 kilometer square, so you will find GST around till 2 kilometer. Okay, so it is not exactly the same. You will find GST all along the, same distance from the MFT. So it is varying if you find depending on the river size and depending on the how much upper Sivalics you have in your catchment. So yeah.
It's, I mean, on geologic timescale, what I'm saying, it has to be, because on the geologic timescale, I mean, you need to reach some kind of study. The only possibility or deviation from this model will be to consider some transient state. So maybe because of the climate, weathering, erosion, or even the disaggregation on the hill slope was different during glacial time and during interglacial, you could observe maybe some transient state and some strange response in terms of gravel-sand transition, or maybe the present sedimentation could be partly impacted by the former geometry of the river inherited from the glacial time. I don't know. Maybe there is some kind of transient effect. But if you are at steady state, no way. I mean, the river has to adapt because it has plenty of load to modify its. If the river has too much transport capacity, no way. It's easy for her to dig and to erode. If the river has not enough transport capacity, there is plenty of load coming from upstream to deposit. So the river will build and accumulate until reaching a profile which is convenient for her to transport the load, the sediment load, the river to transport. So it's a matter of debate and discussion. I would say it's really a way to look at the problem if you look at it as a geologist on a long time scale, or if you look at it as a hydraulic engineer or researcher, because usually people consider that the valley shape it's the bottom of the initial condition and the river is adapting to this initial condition. But if you take a geologic perspective, this initial condition, this plane, it's not random. It's the result of adaptation of the river on the long term to the sediment load coming and the available water also coming from upstream. You see the different perspective? So in this paper, they documented also between the mountain front and the gravel sand transition some decrease of the D50 in black and D90 in white. And there are slight decrease, a slight size reduction by finding, and then again, it's not shown on the graph, some drop with a gravel sand transition that is located at 40 to 10 kilometers from the front. So it is possible to use this kind of distance of deposition to consider that if all the gravel are deposited in between the front and the gravel sand transition, and knowing the created volume for sedimentation by unit of time, so this is the main subsidence rate or the aggradation rate. Knowing this rate, you can compute a volume of sequestration, and knowing the flux of sediments, you can calculate the proportion of bed load in your sediment. So if you do this kind of calculation, you end up with, for large river, less than 2% of gravels compared to the sediment and silt load. With the model, we had a prediction of pebble load lower than 10 to 20% arriving here, and maybe we are underestimating the true abrasion rate. But it seems that the abrasion mill, or the abrasion process, is relatively efficient along these long rivers by reducing an initial bed load proportion or coarse load proportion of 50 to 70%. And when you arrive here, only 2% left, 1 or 2% left, and most of the rest of the load is just sand and silt. So on the mountain range, abrasion is the first order process that modify your size. And when you arrive in the foreland basin, obviously the most important process is selective sorting and makes a very rapid shortage of gravel in your load because of the deposition and further transport of just sand and silt. Okay. And this kind of effect, we can see it also in the past. So when you look at the sedimentary series, if you go from the lower seawallix to the upper seawallix conglomerate, it's quite common to see some relative rapid transition in a few 100 or 200 meters. You go from sandstone to mostly conglomerate with some siltstone layer, but mostly which correspond to overbanks deposit, and but mostly gravel. So 2 orders of magnitude change in sediment size between the sandstone and the conglomerate. For this river, the Bakeya, for the Chure, same thing. I don't show you, but for the Ratukola, same thing. So rapid gravel sand transition. So what we observe today, we observe it in the past. And I show you just a comparison of present river, 2 orders of magnitude decrease at the gravel sand transition. The old Seawallix area, same thing, 2 orders of magnitude when you go from the upper Seawallix conglomerate to the middle Seawallix sandstone. Okay. Maybe we can move to the next part if you have accepted your question.
Now, what you have showed, although these rivers are Himalayan rivers and has lot of sediment, but if we go in some place where we do not really have that much of sediment, like river is not transporting that much of sediment. So how do these slope changes due to less amount of sediments where you actually do not deposit and do not change the slope by depositing? So in case of tectonically inactive areas, or
yeah, if the system is completely out of equilibrium or has not enough sediments to adapt its channel, yeah, the deposition will be guided by the geometry of your channel and the topographic slope.
And what will be the role of the sediments?
The role of sediment, the sediment will adapt. So it's like here, if you during all that part you have some kind of transient response. Let's say, for example, you have this kind of initial bed, and you are activating a new fold. So suddenly you are producing a lot of erosion. Obviously, initially, this river will be out of equilibrium and will be depositing much more here than further downstream. So it is the same if you are in a situation where you are, I don't know, if you arrive, if you build some artificial structure and you send material coming here, that will guide the sedimentation, will be the same rule given by your equation of conservation, or the Exner equation, and will be guided by the divergence of the transport capacity. So here, you know the slope, you know the transport capacity. Here, it's a much lower transport capacity. So the difference will give you the amount or the volume of sediments you are going to deposit in that ridge. So you can predict it if you know the slope, if you know the discharge, and if you know the grain size distribution, in particular the D50, you can calculate it. It's not a problem.
Sediment flux is as far as I understood, a combination of suspended load and bed load. If I want to understand what is the contribution of bed load material from a tributary to mainstream, is there any way to do that? As far as I know, suspended load it is possible. And last time you saw that bed load information is very difficult to estimate. So, or is it a would it make any difference if I am able to distinguish the contribution of suspended load as well as bed load into the mainstream?
It's if you are in the mountain and if the system is detachment limited, that can be complex. If your system is transport limited, for example, if you are in the plain or somewhere here and you can consider it's transport limited, then the input from the tributary will modify the quantity of the flux of sediment. We can modify also potentially the size, the mean size of your sediments. So in some particular case, I presume, but imagine a tributary, a main channel bringing mostly sand, and you have a tributary bringing some flux of pebble. So suddenly you will increase the quantity of pebble. So you would expect at steady, if the river is adapting to this flux condition, you would expect after the tributary maybe to have some increase of the slope, because suddenly for the main river the granulometry of the mean size of the sediment to transport has increased. But if the distribution between the sand, between the main river and the tributary is not very different, or if this is a very small tributary and its volumetric contribution is minimal, it will be very difficult to see any kind of changes. So I would say that if you have a main river with gravels and a tributary bringing sand, you will not see, except if the tributary is huge, a big one. But if the tributary is not, it represents only like 10 or maximum 20% of the drainage area of the main river. If you are bringing sand, I don't think you are going to see a big difference. If at rivers the mainstream is carrying only sand and you have a small tributary bringing pebbles, so that makes a difference that can be reflected in the gradient of the river downstream of the confluence.
Thank you.
Are you thinking in a specific case, or? And the other way to, I mean, obviously, if you are interested in respective flux, for example, a respective flux of bed load, maybe you can be in some kind of favorable case. Let's say all the mainstream is draining schist, and the tributary is bringing quartzite or granite or something like that. So the best way to study what's going on after the confluence is to look at lithologic content of your bed load. If you find 10% granite downstream the confluence, you get a direct estimate. If you know more or less in terms of bed load, you know that the tributary has contributed to 10% to the load of the mainstream. This kind of study you can do.
Thank you. Thank you.
So you mean that grain size can also, difference in grain size can also create a kind of a nick zone or something like this looks like a steepened reach kind of something. So difference in grain size from the tributary can also.
I don't have, it's a purely theoretical. I don't have example in mind, but in theory, yeah. Do I have some example?
And sometimes
Yeah. But there is, I think there is a paper published 2000, 2 or 3 years ago. So if you're interested, maybe I'm wrong, but I think it's a paper where one of the researchers, Finnegan, and it's Western US river. There is some river draining some schist or something like that, and there are rivers, tributary draining some diorite, I think, or maybe granite. And it seems to me that, so it is flowing that way. And it seems that after the arrival of the diuretic material, which is bringing much coarser bed load, then they observe some nick point. I'm not sure, but maybe you can check, and I can check later. In the long-term history of the, yeah. 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 Obviously. Well, I mean, it's, I don't have a, I don't have data directly to show you. Well, first, you can have some climatic variation and some change of channel geometry on short term that can modify this distance. And Rajiv Sinha has done several years ago some cores in the Cosifan, somewhere here, I don't remember, let's say at 100 kilometers, no, maybe 50 kilometers from the front. And from what I remember, sometimes he found some level of gravels in that part. So maybe with climate, it is something which has been changing. At the broader scale, Shillong Plateau, this is the Himalayan northeast syntax. People have been doing, in particular, a US researcher has been working quite a lot in the Ganga-Brahmaputra system in that area, and he has been documented some reincision of the Brahmaputra 10,000 years ago, and at the base of this unconformity, which is 11,000 years old, it seems to me, so you get some old material re-incised and recent alluvium, and it seems that, no, not here, he found some gravel at the base of the core. So I don't remember if it's like 70-meter deep. So this is some kind of canyon due to the fact that the sea level during glacial time was lower. So the Brahmaputra and the Ganga have insides made this kind of canyon in the former sediments. And one interpretation, or my interpretation for the gravels, and they are proposing a different one in, I think, in this paper by Goodbread and his co-author. In the paper by Goodbread and co-author, they are proposing that there was some big glacial lake outburst flow in the upper Namche-Bawa area that brought some massive debris flow and heavy loaded flow that brought this coarse material down over a distance of 800 kilometers. My interpretation is different. It's because you have this kind of incision canyon, so there is no more subsidence. So no more aggradation during the incision phase. So no space to store your gravel. So your gravel, you can, in particular if they are quartzite, I mean, if they are schist, they will be destroyed by abrasion. But quartzite, you can transport over long distance. So my interpretation, it's again the same kind of phenomenon. If you don't have aggradation, the gravel sand transition can be far away. And if you go in the places like the western US, on the Piedmont, the Rocky, so there is a formation, a conglomeratic formation, Wallalaga, I cannot pronounce it correctly, it's an Indian name, I think, and the North American Indian name. The distance of transport of gravel, it's over, I think, almost 100 or maybe more kilometers. So the gravel sand transition can be very different in different settings, in particular if there is no space creation for long-term aggradation. Finally, to finish with your question, so you can have climatic variation, so climatic and temporal variation of your gravel sand transition, and otherwise for the long-term evolution of the system. So here you have the front. Here you may have, well, depending on variation, the gravel sand transition. And then, let's say, you have initiation of a new fold. So a new fold because of the convergence between India and South Tibet is keeping on. Then if you have, as Mr. Day called it, in sequence propagation, so you initiate a new fold, and obviously once you begin to have a new topography bringing sediments, then you will create and shift by the same amount, more or less, your gravel sand transition. So on time, we can imagine it has been migrating like any kind of a facies. It has been migrating southward. So to finish, I will Vikrant asked me to make some kind of presentation of the experiment. So it will be of the experimental work. So it will be a presentation which is completely not exhaustive. And this evening, you will get a lecture about experimental work dedicated to sediment transport, I think, and hydraulics. So I will not be doing a review of what has been done in earth science and in particular in geomorphology. I will give you just a few hints of the work that can be done, and I will show you the experiment I've been developing, but just as a matter of example of the things that can be done, the variable that we need to be measured, and so on. So first, what is the interest of doing experimental geomorphology? We saw that in some cases, bed load is extremely difficult to measure. So it's difficult to measure certain phenomenon directly in nature. For bedrock erosion, we saw that it's probably in many cases it's a few millimeters per year, so it's a slow process, so it's difficult to track on a short-term project. There are many coupling between hill slope and erosion, so we saw that the grain size can evolve along the river in size and destabilize the hill slope. So all this kind of thing of coupling makes the system complex. So sometimes, in order to be able to model and to see what's going on, it can be interesting to do experimental work. So experimental work, there are two kinds of experimental work. The one you just try to reproduce roughly some process without trying to make some scaling of the physical variable. So this is the case, for example, in this tank. It is full of sand. There is the experimentator is pouring water, and you make some rills and some drain, some crest, and it almost looks like a landscape. So it gives you some idea about how forms the landscape, how possibly it can evolve, what is the mobility of your drainage. You are not even sure that it corresponds to nature, but it can give you some idea what's going on, and then you can go back on the field and, oh, let's try this idea. You can go to slightly some kind of scaling attempt. So in that case, you will try to adimensionalize important variable, or the variable that seems important for you, to try to make some correspondence potentially between your experiment and some case study. So for example, I mentioned this study from Buffet and co-laborator in 2016. The idea was to look at the interaction between streams. So we are in the southern Tian Shan. You have this nice fold, growing fold, and you have the river coming from Tian Shan. At the same time, they are depositing. When they cross the active fold, they have to cut. And if they are active, they can just go from the right to the left and bevel some kind of wide channel. So intuitively, you are thinking, if the fold is growing fast, the river has less time to go left and right and to bevel a large valley. So maybe by looking at the width of the valley, we can get some idea about the uplift rate of the fold. But obviously, it will be depending also on the sedimentation rate or the regional sedimentation rate. So in order to try to answer this question, for example, they build this kind of model where the pile, they put some sand and some system to create uplift like for a fold, and they will vary the quantity of sediments and the quantity of uplift. And then, if you're interested by scaling, you can look for the variables. So they found, for example, two variables. The quantity of the flux of sediment rework that will be depend on the time scale of the migration of your river, and compare with the tectonic flux, so the size of the uplifting zone multiplied by the uplift rate. And in the case, we see some kind of linear relationship, or no, logarithmic relationship between this non-dimensional flux, between the rework sediment flux and the uplift flux, and but they compare with, for example, the size of the beveled area. So if it's correct, they can go back to the field, and given the size of the valley which is beveled, they can get some idea about the uplift, if obviously they get an idea about migration and sediment flux. So it's one step ahead compared to the non-scale attempt, because here you can maybe go back to nature and quantitatively make some transfer of quantity and some quantitative comparison. Well, I didn't say that, but so typically you can have any kind of experiment in earth science and geomorphology. Some people have tried to model the whole mountain with a pile of sand. Some other have focused on just the piedmont. Some other have just looked at the behavior of the floodplain and the behavior of deposition of the braided system. And you can go at smaller and smaller scale. And in particular, we have been using a straight flume just to look at the sediment transport. So you can look at sediment transport at the scale of the braided system or at the floodplain, or you can look at a smaller scale just to understand, for example, the pebble trajectory. And so it's more like a straight flume, like the one we will see this afternoon. So this kind of flume, or here in St. Anthony Falls in Minnesota, where there is part of the Mississippi or Missouri River, I don't remember, which is diverted and brings all the flow or the water available for very large flumes. So the flume, in general, it's a system like that, with some wall transparent in general to be able to visualize. And you can have different system where you can, well, most systems have a recirculation of water with a pump. And some system you can even recirculate the sediment with some different pump or with some belt conveyor. So you can be in a closed circuit. If you want to scale your model, you need to verify some condition of similarity about the hydraulics and about the sediment transport. So people will be trying to respect in between nature and the model they are using to try to reproduce the natural phenomenon they are studying. They will try to keep the same, what we call Freund number, which is U to the square, which is a flow velocity over G and H water depth. They will try to respect also Reynolds number. So whatever is full Reynolds number for the flow, or the grains Reynolds number, which is applied just to the grain. So most of the time, this Reynolds number makes a difference between laminar flow and turbulent flow. And most of the time, it's quite an easy condition to respect. Shield number for sediment transport. So if you have a small size scale flume and you have obviously lower shear stress, then you will be working with a smaller grain size in order to get the same shield stress as in your natural system. Rose number for suspension, and for transport capacity, Einstein number, which is, so Einstein from the sun, sediment flux divided by the difference of density, and G multiplied by the cubic power of the grain size. You have to care about the boundary condition. Typically, I was mentioning that some system can recirculate the sediments, and some other, it's without recirculation, and it's just a feeding system. So depending if you are feeding the system with always the same grain size, or if you are recirculating the sediments, you will don't get the same result. Because, for example, here, if you are a lot of gravels and a few sand, so let's say all the sand is kept in the porosity of the gravels, in the void between gravels, and if you have water flowing like that, not sufficient with a slope, not enough to move the pebble, then what is leaving from here is just clean water, okay? So if you recirculate sediment and clean water, there is no sediments coming back from here. So basically, you don't recirculate anything and you don't change the slope. If you have a constant Physique system, then whatever it's leaving the system here, you are piling sediment, adding. So the slope will be increasing because you are aggrading. So just an example about the fact that changing the condition, the recirculation condition, will change the final result. So it's important to choose your analogy in function of what you want to model. So again, the shear stress, the transport capacity depending on the shear stress. So the variable that you want to measure and control in your flume will be the water velocity, potentially the shear stress, water depth. With water depth and slope, you can also calculate more or less the average shear stress. Potentially, you want to describe the pebble trajectory and also to follow the sedimentation of the degradation, or maybe the channel position, looking at bed topography and sediment cover. So there are different instruments to do that. For water, you can, for example, use laser Doppler velocimetry. You can use also, for example, a laser sheet with your sediment loaded with a small particle, a small thin particle with the same density as water. So you will get in your light the trajectory of this small particle, and by looking and doing a particular tracking analysis with your high-speed camera, you can get an idea about the water turbulence and also of the mean water velocity. So an example of this thin particle in the fluid that give you an idea of the trajectory of the fluid, within the fluid. You can, if you are interested of what's going on your pebble, you can install also pressure sensor, stress meter, and get an idea about, through time, the effect of the turbulence on the variation on the force acting on your pebble. For the bed, I will not show it, but you can measure from the top with different techniques. It can be with a camera and a system of stereogrammetry to measure the position of the bed. You can also have a distance laser distance meter. If you're interested in bedrock erosion and pebble abrasion, as I was, you can go through a straight flume, which is a flume which is used by most hydrolicians. So it gives you some kind of, people have been using this kind of flume for years and years, so it's well calibrated. It's relatively realistic in comparison with natural system. The problem if you're looking, for example, for pebble abrasion, it's difficult to make the pebble running for kilometers to see significant abrasion in such a kind of flume because it's traveling, let's say, 10 meters, the length of your flume, and then you have to take your gravel without modifying it, without abrading, and put it again at the beginning. So, and for 1 kilometer, you will have to do it 100 times. So that makes the things quite difficult, except if you have an automatic recirculating system. Otherwise, you can go through recirculation system. The advantage, you can do long distance transport without any problem. No need to manipulate huge quantity of sediments. If you have a 10-meter long flume, 30 centimeter wide, then you need several cubic meter of sediments to have a significant layer of gravel. in recirculation system, it's smaller surface. You don't need to manipulate so much sediment. The drawback, it's not as realistic in terms of sediment transport. And in the one I will show you, for example, in annular flume, we cannot get rid of some centrifugal forces that makes the sediment transport not as similar as in straight flume. So still, straight flume has been used to, for example, document the evolution of alluvial cover on bedrock. It can be interesting to document the cover of the two effects. So supply that vary between 0 and 1, fraction of bedrock exposure. So supply, almost no sediment arriving in the system. All the bedrock is uncovered. You can see the bedrock, and the larger the quantity of sediments you are bringing in the system, the more the cover of sediment. You can decide to put very weak concrete in order to see significant abrasion at the scale of your experiment, at the time scale of your experiment. It's already what I have shown with the result obtained by looking at sediment concentration, looking with the camera and measuring the erosion substrate with a laser. I explained the dual role of the sediment that can be evidenced with this kind of flume. Then, if we are interested, as I was saying, by pebble abrasion, you need to go to recirculation system. So there are different recirculation systems. The first one, or most basic one, is what we call the tumbling or rotating drum. So it's just a cylinder. You put your load with some water, and you make rotate. So by making rotating, you get some abrasion. It's like the Los Angeles triol, except you don't put iron cast. You make turn, and you get abrasion. But it's difficult in this kind of system to have high energy impact. So for example, Kodama in 94 introduced some small, how can we call that? Small part that will inhibit the sediment to slide, and it's only when it's arriving high enough that it will fall down. So in that system, he was able to have not only friction like that, but also pebble impact by free fall. And he was rotating slightly faster. But in all cases, I mean, it's relatively poor reproduction of the alluvial transport and alluvial dynamics. It was part of the problem that was maintaining, discussing the geomorphologists during many decades. With rotating system, rotating drum, usually people were ending with relatively low erodability. And when they were comparing with fining rate of order of 10% decrease per kilometer, there is this mismatch by 1 to 2 order of magnitude that was not explained. So people were considering that abrasion was not important, only sorting. Then Kodama made some slightly more energetic experiment, was able to reproduce higher abrasion rate. But because it was not sufficient to reproduce the alluvial transport and the sediment transport, people went to other systems. So it's a view from the top in the two cases, and it's an annular flume, and this is a section. So two annular flume where the pebbles are traveling at the bottom. One system where water entrainment is made by how we call it churn. I don't know exactly what we'll call it in English. Propeller, the churn. Yeah, but they are vertical. Propeller, it's more like okay, churns. And in this system, there was water injection at the base. This system was having a problem because just behind the churn, it produced a lot of turbulence, and potentially at high flow, you can have interaction of the pebble with the churns. And here, there was some limitation with this system, with a pump inside at the middle of the system. There was a limitation in terms of velocity that can be reached. Some simple device where this time it's a propeller. So this time it's not annular but a cylinder, and the propeller will make the water turn and make some entrainment at the bottom. So we were in the position to decide which device we wanted for our study. So initially we wanted to study pebble abrasion and potentially also bedrock abrasion. So we wanted some system hybrid that make able the possibility to look at the two processes. We wanted to have the possibility to look at large pebbles, so to be able to entrain and move pebble up to 10 centimeters. So we wanted high water velocity. So according to our needs, we decide about what was the technical answer, and according also about the available place and about the price or the money available. We decided to do some flume with lateral injection. So first, before building a large system, we made a small scale model in order to get an idea of what's going on, how the water is going to behave, if we put small gravels, how it works. Looking with the light system and the tracer, get an idea of the trajectory of the fluid. And then, after this first step, trying to understand at small scale what's going on, we can go to the building, to the larger device. So I already shown it. The flume in itself, in steel, some window to see what's going on. For injection with the water driven by a pump, sent in the 4 injection. The 4 injection makes, tangential injection makes the flow to rotate and make some entrainment of the pebble at the base. And the water will fall at the middle part, fall in the tank, and then it is recirculated by the pump. So recirculation of the water, but the coarse load, the pebbles, are staying all the time in the flume. Obviously, we'll be producing by abrasion suspended load, so the suspended load will follow the water and is recirculated also by the pump. And some of it will settle down in the tank and will stay in the tank. Again, in cross-section, the water speeding in the center of system. At low flow, moderate and high pump discharge. So high pump discharge, you see a kind of vortex due to centrifugal forces. So then, in order to do parametric studies, you need to know the variable you're interested in. So for example, the water velocity, the pebble velocity, the shear stress. So there are several ways to measure the velocity. In this case, we use some pitot tube to make at different depth the measurement of the velocity. Sorry? I'm sorry. So you see that This is the profile of the water for a given pump discharge, 2 to 2.5 meter. So instead of having the flow entrained by gravity, like in a natural river, the flow is entrained by the injection of the fluid, but the effect on the gravel will be the same. The drag force of the fluid in motion on the pebble at the bottom will make the entrainment of the... Oh, you were saying the effect of the fluid or of the centrifugal force?
Yeah, means at the base you are considering that speed of pebble and water will be the same.
No, no, I'm measuring the pebble velocity.
Okay.
Oh, sorry. So we can draw a map of the velocity. So we can see if at high velocity, high pump discharge, we get some relatively homogeneous or uniform tangential velocity or fluid velocity. At low flow, at very low pump discharge, we begin to have some gradient due to the fact the water is going faster in the outside of the film than in the inside. So usually it's not what we want. We want to have uniform condition. So we have been avoiding to work at low pump discharge. We have been working only at high pump or moderate pump discharge. We can calculate the shear stress using a Euler equation. I will not come into the detail. So it's just the mean fluid velocity in function of the injection velocity. So there is an increase, but you see that depending on the quantity of sediment and depending on the gravel size, it will modify the relation. Just because when you consider large gravel or small gravel, the friction coefficient, the roughness of the bottom is not the same. So for a given injection velocity, so for a given pump discharge, then for large pebbles, you will get lower flow velocity than for small pebbles, just because the roughness is not the same. So there is more friction by large pebble than by small pebble. Anyway, you can calibrate it. So there is a way to get the shear stress for any kind of fluid injection. Then I show we can follow the pebble trajectory. So there are the mirror here, and there is one basal mirror. So we put some mirror at 45 degrees to be able to see from below and have the movie at the same time of the motion in the vertical plane and the motion in the horizontal plane. So we can know the trajectory in the vertical plane, and we can know also the trajectory in that horizontal plane. So we can know, for example, if there is a good distribution radially of the pebble. So we arrive to your questions. So we can track on the high-speed camera, so manually, or if we have an automatic system, we can look at the trajectory. And so we can know the saltation I. We can look also at the length of the saltation, and obviously we can look at also the velocity, the pebble velocity. We have done also different counting for the pebble velocity. We can put, for example, a colored pebble and count how much time it takes to make 20 round trip. Or more recently, we have been using an electromagnetic system. So we put a pit tag, electromagnetic pit tag in a pebble, and we have an antenna, and we count each time the pebble is coming in front of the antenna. So you can get some statistic about the mean velocity, and also if sometimes at low flow the pebble is resting and then moving again, resting, and then you can have the statistic of the lap time, and you can use this kind of information to compare, for example, with natural system. Or you see it's for smaller pebble size, and the water begin to be turbid because we had run several experiments before, so it's becoming more difficult to track the things. We can also just count the number of pebbles and get some concentration. So this is for 1 2 centimeter pebble and 2 4 centimeter pebble. You see that the 1 2 centimeter pebble, because they are smaller, they can travel slightly higher in suspension. Obviously, you have to care about boundary conditions, so you can put different type of boundary condition. Here it's non-abrasive, it's tires, but you can choose also to glue or to put pebbles and get some abrasive bottom. And obviously, if you do pebble abrasion on abrasive bottom, you will get higher abrasion rate than if you use non-abrasive bottom. Different way to measure an abrasion. You can just, if you have a plate, you can compare the topography of your object before and after. If it is a pebble, the simplest way is just to weight your material, your pebble, introduce it, not shake it, but make it turn, and wait just after, and the difference of weight is just the abrasion. Very simple. So as I was mentioning, this relative to the relation between abrasion rate and velocity, you see that here we have some kind of relation that say that the erosion or abrasion rate is scaling with a power. How do we say in English? Oh. Yeah, square. Yeah. With the square of the pebble velocity. So the higher the pebble velocity, the more energetic are the impact, the collision, and the higher is the abrasion. So you can, but the great thing with the experimental work, you can do parametric study. So you can decide to maintain everything fixed, similar, bottom condition, pebble size, sediment quantity, velocity, and you will just modify the water velocity. You can decide to maintain the same pebble velocity or water velocity and just modify the gravel size. And then another bunch of experiments, you will modify just the quantity of sediment and so on. So that way it can be done for pebble abrasion. It can be done also for bedrock abrasion, as I already shown it. So you can vary sediment quantity, you can vary pump discharge. Another example where the shear stress condition is varied, and here the gravel quantity is varied, so you can see how erosion is modified, be able to compare with simple mechanistic model. And you can do any kind, well, depending on your device and depending which process you're interested in, but you can imagine many kind of different parametric study. So you can also look at the angle of impact. So look, if you put the plate horizontal or if you put the bedrock plate at 45 degrees, you may have a look also at the small scale process. So here it's just an example of an optical profilometer to document the abrasion. So we don't see so clearly, but you see here small fracture, microfracture created by the impact of a pebble on a plate, bedrock plate. Another example I already shown you, some crater, some zone of undimensionment and fracturing and removing of mass because of the impact. So it's 2 millimeter wide. Obviously, you can, in the parametric study, test also different lithology and make comparison with some mechanical resistance. So it was been done by Sklar and Dietrich in 2001 or 2002, I don't remember, in the small cylinder abrasion mill. They compare different lithology, and they obtain some kind of relation between erosion rate and tensile strength. So in the flume, we can do the same, whatever it's on the pebble plate, on the gravel erosion. And in that case, it's for gravel erosion. And we observe more or less the same exponent. So gravel is erosion or abrasion is decreasing by a power minus 2 according to the tensile strength. You could, I mean, if you're interested in the evolution of the pebble, you can also look at the produce of the fragmentation and the attrition. You can modify also the gravel size. So here, from 2 millimeter to 25 millimeter. And then, once you have compiled and made several experiments, or before that you have to think about it previously, you need to think about the scaling and also how you go from your experiment to a natural river. Because if you have been working with 2 centimeter pebble, how do you transpose your result to 20 or 30 centimeter pebbles in nature? And you see it's not always very obvious. This is gravel size, erosion rate as a function of gravel size for the bedrock. This is Claren-Dietrich experiment result, small flume, large flume. So they are not on the same scale, but they were done at different velocity. So maybe, but if we scale correctly the effect of velocity, maybe by an exponent of 2 or 3, we'll be able to reconcile the 3 set of experimental data. Another problem with the scaling, not with hydraulics, but this time with really the mechanical part. We have been comparing, for example, abrasion rate on pebbles in the small flume and the large flume. So normally we would expect some linear relationship with a factor of 10 because the pebble velocity is not the same here and here. Here it's much slower than here. But you see that there are a number of points that deviate this linear agreement. And the explanation is because at higher velocity you have more fragmentation, and for larger size also. Then in the small flume we have only abrasion process or attrition process, and in the large flume we have attrition plus fragmentation, in particular for some specific lithology. So in that case, the scaling between the small scale and the large scale, and it could be the same going from the experiment to nature, can be difficult because we are looking or we are incorporating 2 different processes in a different manner. No fragmentation, significant fragmentation here. So sometimes that can make the transposition to a natural system quite tricky. So in that case, it's interesting to have 2 devices of different size to see this kind of problems that can be arise. The experiment, so it's nice to do parametric study. It can be useful also, and it is the case in the lab here in IIT. It can be used also to test sensor, apparatus, system that will be launched or that will be installed in natural stream. So in that case, I've shown the first day this system of sensor to measure erosion rate. Before installing in the field, I had tested first in the large flume, inserting this kind of system at the base of the flume to see if I was recording correctly the voltage and what was the behavior of the sensor. So here they are, and we'll see this afternoon, they are testing system to measure bed load with accelerometer sensor or shock sensor. And typically the idea is the same. They test the system in the flume. They try to calibrate the acoustic noise they measure in function of the sediment load transiting on top of the plate, or depending also on the pebble size. And once they have calibrated, they got a better idea of what they can measure in the field. So to conclude, well, there are different issues, some difficulties, scientific difficulties. The most difficult one is the dimensionalizing or the scaling of some processes to go from the experiment to nature. So it's something you have to care about. And in terms of practical conclusion, it's really, it's a richness to do experimental job, because by looking directly at the processes of the phenomenon, you understand better what's going on. And if it's a process difficult to measure on the field, then it's a nice way also to do parametric study. But sometimes, I mean, you need to develop sensor to measure velocity, pebble velocity, this kind of thing. So you need, and you need to find some technical solution. Not always obvious, because sometimes, I mean, your water is turbid, so it's not easy to use a particular visualization set. You need to use something else. So it's really important to have some kind of technical or engineering support to bring you any kind of technological solution to solve your problem. So very rich approach, but it can be time consuming, because doing experiment takes time, and even building the device, if it's not a commercial one, will take a lot of time in order to get something useful for your research.